When I was 6, my father tried to teach me gate logic using AND gates and NAND gates and so forth. And I actually understood the binary side of it, but I didn't understand what the breadboard was for. Because I looked at it and I'm like, well, how does this translate to the stuff you just drew on paper? And ever since that moment, for me, it was about the logic side, the software side of technology versus kind of physically putting it together after drawing it. So needless to say, I picked up development at an early age, and I knew right away that I wanted to be a software developer, even before it was cool to be a software developer. This was like the early 80s when software developers didn't make any money, and they were like, people that you never even heard about. And lucky for me, 30 years later, we're like the coolest people in the world now. So that's really awesome. So you can call that foresight, I guess. So anyway, my presentation is titled Winning the Future, and I'm actually really passionate about this topic, and it's really kind of a software view of what we've heard a lot about this morning, and I'm excited to be presenting it to you. So I say the future of not long ago because HAL 9000 was really, I'm sure you guys have all seen the movie and read the book and so forth, and Arthur C. Clarke's amazing story and Stanley Kubrick's incredible screenplay based on it. But at that point, when I saw this movie, 2001: A Space Odyssey, when I was a little kid, and it was already several years, many years old. The film was made before I was born. But I saw it, and it's an interesting story because we didn't have cable. So it was actually being broadcast on broadcast television back when you had 4 channels on TV, right? And the really amazing thing about it was that it was being broadcast in stereo. This was 1983, maybe, where that kind of thing was almost unheard of. So my dad, we didn't have cable, and my father kind of rigged together an amplifier and a receiver because, of course, our TV was not a stereo TV. Nobody had that stuff back then, or at least we didn't. We weren't wealthy enough to. And we saw this film, and of course, my parents hyped it up tremendously because they actually saw it before they got married. They got married in 1970. The film came out in 1968. They saw it in the theater. They were blown away. They're like, "You're going to love this movie," blah, blah, blah. Well, I was blown away, and it had a profound influence on me. And there were 2 things that really just, amazed me the most about the movie. And then I've read a lot of Clarke's books and so forth. One was the monolith. I mean, 1x4x9, perfectly black. What can you not like about that? But the second thing was obviously HAL 9000. And, at that point, HAL 9000 represented the future of computing. And I say at that point, but it really went on for 40 years, from the point where it was kind of, envisioned. It was an awesome, foolproof computer system, right? And I dare to say that it also made a tremendous impression on a lot of other kids at the time. Because, people that kind of I grew up with that were into computers, that was kind of the benchmark for us. If we're going to build a computer system one day, we want it to be like HAL 9000, right? Because it's just, there's nothing more amazing than that. But, as much as pains me to say this because of how much the affection I have for HAL 9000, HAL was really the future of the past. And, a lot of things changed since then. And you might recognize the movie quote there, but let's not forget that something went terribly wrong with HAL, right? We really had to think about the future a lot more after we envisioned that. And one, it did a lot of great things, but it also had some major flaws. For example, it murdered an entire crew, killed an astronaut, and then it had to be shut down to not kill the other astronaut, who then went off on his own crazy trip. Basically it was, in that sense, it was kind of a foreshadowing. I don't think it was really thought about this way when it was envisioned, but what happens when you put that much power in the hands of this machine? And it's not so much about that concept as more about the architecture of the machine, right? So let's see what I like to say, what the future actually got wrong, right? So the future of 1968 was monolithic. It was bulletproof. And it was cognitive. So the cognitive part didn't get so wrong. But the other 2 parts, if you think about it, HAL was really just a mainframe. And it was kind of the epitome of the mainframe. It's what the mainframe, people's wildest dream about the mainframe was well, that's what it's going to end up being, right? It was this massive sort of monolithic system that never failed. In fact, HAL would tell you directly that no 9000 series computer had ever made even the slightest calculation error, et cetera, even though then it went and killed 3-4 people, but whatever. basically it was like the vision of the future was the vision of the present kind of taken to its extreme. And a lot of times, one of the things that happens to technologists in general, and if you're not bound by this, you're thought of as a futurist. So then you're kind of put in that bucket where you're just some crazy freak who like envisions a future that we can't even imagine. But we are bound by the limits of our understanding. So, and it's not necessarily something that we think about consciously. We make a decision that says you just can't do that, and whether we make it consciously or unconsciously, it kind of dictates our vision of the future, right? So obviously, if our view of computers were that the only way to get power was to build these massive mainframes, there's no way you're going to have microcomputers that can do this. Then obviously our vision of the future was going to be an even bigger, more powerful mainframe, right? And interestingly enough, it wasn't until like well into the 2000s that this started to change, that the vision of the future started to change. I mean, the server-based computing of the 2000s that we all invested so much of our lives in, I certainly did, pushing kind of images out to thin clients and centralizing all the processing. Well, that was obviously a different incarnation, but it was the same basic idea. It said, hey, you're going to have this monolithic system, and you're going to centralize all the state, and everything's going to be great. Of course, what we learned painfully is that the market pretty much rejected that, and then something came along and kind of crushed it, and we'll talk about that in a minute. But it took about 40 years for that vision of the 1968 future to change drastically, right? So the 2016 view of the future is obviously, very different. One is obviously it's distributed instead of monolithic. It's also designed to fail versus being bulletproof. So now we actually understand that computers fail all the time, and it's way too expensive to try to make them like completely impenetrable. So instead, we kind of do things like replication and statelessness and et cetera, and build algorithms that can actually tolerate failures. They're fault tolerant versus foolproof type systems. But the cognitive part obviously was the one area that being able to build new processes by learning on existing processes, that's kind of the foundation of AI today, right? So it didn't get it all wrong, but obviously, the first 2 points were wrong. And a few years ago, something really big happened that kind of led to this whole new direction. And really, it's mobile. I mean, mobile kind of changed the face of computing, I would say, for like the next era of computing. And remember, mobile in Hal's day was the eye inside a space pod that communicated back to the central computer. That was mobile. It was basically a receiver for the central system. Well, mobile today is about processing on the edge as well as collecting data. It's a very different use case. And when we think about, what do you mean processing on the edge? Well, this is like a $300 phone, and I've got 6 cores, 3 gigabytes of RAM, and I've got like a 192 core GPU on here. And it's like, well, why would I just use this to browse the web? You can obviously do a whole lot more on this device. And that's really, and for the price of less than a terminal cost back in even 10, 15 years ago, right? So that really changed a lot of things. We had to think about not just distributing like within the internet context, but also distributing all the way to the edge and building algorithms that could handle data collection from heterogeneous points and so forth, right? The other thing that's really important about the 2016 future is, and we've heard about it this morning in several different ways, is that it's very accessible. In the 1968 version of the future, you had to be a researcher and a very elite researcher to get your hands on anything approaching HAL 9000, right? Now, and there's nothing wrong with that. Researchers do great work, but we believe that by democratizing resources, you can inspire innovation from places where you wouldn't normally think, right? If necessity is the mother of invention, you want to get these things in front of as many people as possible who have practical problems to solve that may lead to the next breakthrough, right? So why limit it to that very elite community that can afford or have access to these systems? We've moved into the era of predictive analytics and being able to kind of, instead of being prompted to tell us an answer, and we'll cover that in a minute, is the computer just basically collects data and decides when it's time to prompt us for, with data, right? With more data. It's kind of an extension of cognitive. And of course, heterogeneous, because by nature, the fact that we have all these different classes of devices, both collecting and processing data, we can't simply build algorithms that work on specific machines anymore. Even if we use high-level languages, as we've seen, this morning, there's a lot of benefit to using more kind of, domain-specific technologies, or even like accelerator-type technologies that need to work on different types of systems. So one size doesn't fit all, and the future that we believe in and that Nimbix believes in is that the seamless hardware and software integration on a per workflow basis is really what's going to win the future for us. What's going to say, you know what, this algorithm works best on that type of system, and just go and do it, versus let me build a computer to solve these problems, right? Which is kind of the way we would do it in the past. And this is a kind of an illustration of what AI has become, and I think we're all really familiar with both the left and the right of this, right? In the 1950s, like when Alan Turing imagined a Turing test, right, in 1950, it was basically like, okay, you were going to have a conversation with a machine, and you weren't going to know that you were talking to a machine, but you had to obviously prompt the machine would tell you stuff, and you would think you were talking to a human. And in a very simplistic example, what happened there is the guy missed his meeting because he had to ask the machine when his next meeting was. And by the time he asked the machine, it was too late. He wasn't going to be able to make the meeting, right? Where in 2016, we all see this now with Google Now and different apps. It just pops up and tells us, hey, you need to leave in like 10 minutes if you want to make the meeting downtown. And I didn't have to tell the system anything. It already knows because it has the data, it has the analytics to actually do it. And instead of burdening me with having a conversation with it, it just tells me what I need to know at the relevant time, right? And then very soon, it's also going to take into account things that may not even be relevant to our meeting, right? It may just simply know that we like statues or we like sculptures. Why? Because we search for sculptures, right? And we search for sculptures by a particular, artist, and it happens to know that they just put a new one in the square, so we may want a few minutes to just stop and appreciate it, right? So this is, I say very soon. I mean, the technology is already here. The question is, are we going to actually aggregate the analytics that way anytime really soon? So the bottom line is that you can simulate a human conversation. It's not easy, but with the resources we have today, you can probably trick someone pretty cost effectively into thinking they're talking to a human. But the AI direction that really matters now is processing data that, you just imagine having like the ultimate personal assistant that just knows everything, and without you even having to ask him or her anything, he or she just tells you whatever you need to know when you need to know it, right? That's what AI has become now. And a really important element to this is what I call the dynamic nature of data. And, we talk about this all the time, that, data used to be something that we indexed. We had this massive amount of data, and the challenge was searching, was like finding information, right? So we optimized systems like, binary search space and so forth to find kind of needles in a haystack, and not so much worried about inserting needles into a haystack. That part was always kind of left behind as like the slower part of it. And now it was all about like, well, I want to find this one piece of information. Well, so we had professions like data entry, like people would actually sit there and take a paper form and type it into a computer, right? Because that's kind of how data was created. And then we had data management. We had DBAs who were really just paid to index databases and to create indices for databases, because that made search go faster, right? And now that's kind of been replaced by what we call very broadly unstructured data, which is data. The data is already there. You don't have to enter it. You have to aggregate it. You have to filter it. You have to capture it, but it's already there, right? And data science replacing data management, as something that's happening right now and will continue to happen. So really deriving insight from data versus trying to find data, because finding data is just not that interesting anymore. That's kind of a given. Any system can find data, right? So what happened? First, the increased rate of data collection is basically just off the charts. So instead of spending all our time trying to structure it, in a way, I don't want to say it this way, but we kind of gave up and said, you know what, we're just gonna take it and work with it, right? Whichever form we get it, so that we can actually process it, move on to the processing, which is the important part. The second thing that's really key here is that data actually has a half-life, right? It's always being replaced with more relevant versions of itself. And I use a really morbid example here that I love to use, and it's gonna, maybe anger some people, but if you're fighting an epidemic and everyone's going to die, you want to find a cure before everybody dies, right? So being able to actually, again, if you find a cure a day after everyone's dead, it doesn't matter. You have the data, you have the right answer, but it's too late, right? So again, we can't be bothered with indexing and structuring data. We have to use the data that we have on hand. So yesterday's data has little meaning, so it's really analytics that matter now versus actually indexing data and so forth. And then the other thing that's really important is that big data goes hand in hand with mobile, with IoT, and with cloud, because obviously you have all this data collection happening from all over the place, and on top of that, you need to be able to process it in a very elastic way. So that these things are all kind of related now. So again, you're not hitting a monolithic database engine that doesn't really change very much. Your customer data pretty much stays the same, like back in the 10, 15 years ago, and you're searching for like somebody's social security number based on their last name, a very common case. And now, yeah, that data's still there, but there's so much new data coming in that's way more relevant. And a lot of it's the result of analytics that were, executed on sort of data that existed before. So the conclusion that I think we all are arriving at and have arrived at is that data is really the foundation of AI. So AI really means deriving insight from data, right? We talked about what another way called the time value of data. It has a half-life and it must be processed before it actually decays while it's still relevant. And it's all over the place, right? I mean, you have social media, you have location data, you have search history, et cetera, but you also have traditional data, and you have reference data as well, especially in certain domains. You're always going to have reference data, right? If you're doing genomics, you're going to be searching on the reference, human genome data. But again, without the more dynamic data, you're not really doing anything that interesting, right? And that's where really the foundation of AI lives. And kind of one thing that's happening as an example is we learn a lot more from what people say about themselves than the data that we collect about them. So if you really want to know what somebody's interested in, just look at their Twitter feed, right? Versus ask them a questionnaire, in which case they'll either they'll lie, they won't be prepared, or they'll forget something or whatever. Just look at their social media habits. You're going to learn a lot more about them that way. And that data is already there. You don't have to take the time to collect the data, right? So if we think about, what is the future of computing, it starts with massive amounts of unstructured data. It comes from many sources. It evolves by the minute or even the second or eventually even the millisecond. And it's in many different forms, right? The next thing is the high performance analytics. You want to analyze the data while it's still relevant, not sometime in the future when it's no longer relevant. So you need computing power to actually do that, and you need algorithms at scale to be able to do it. And then finally, on-demand execution, right? There's two ways to do it. One is implicit. You want a cognitive system that actually just kind of does analytics and tells you stuff, which is what we're growing accustomed to. I'll never forget the first time that Google Now prompted me. I was completely freaked out for like maybe 15 seconds until I realized, oh, it has all that data. It didn't just kind of make that up. That's all obvious from my data. But the first time I saw it in action, it was like, whoa, what happened here? How does it know I'm here? How did it know I'm traveling at this speed? All this stuff, right? But that implicit on-demand execution, and obviously we don't want to pre-process all the data and have it handy because, again, it changes so often that you need to be able to do it on the fly. That's why you need the on-demand execution. And then there's the explicit nature of it, which, which is the actual data science part, where you actually have data and you want to derive insight from it. You say, well, what if I looked at this? And that's more of an explicit thing. But again, it's an on-demand process because some of the analytics may take a handful of machines, and some may take thousands of machines. And what you don't want to do is build an infrastructure that, is designed for kind of the worst case scenario and then never use it, right? So you want it to be on demand. And really, if we really think about it, this is already in our grasp. The technology is all here and the future is ours. So now we can just go home and be happy, right? So how do we win? We focus on high performance analytics because that's the one part that we have to build. The analytics change all the time. And that's what we really have to focus on to derive new meaning from data. So we get the data for free. We get on-demand execution from the platforms we use. So we must really focus on building analytics. But this is what the present actually looks like. When you think about, kind of the more, maybe some of the more popular cloud offerings that are out there or whatever, you have to manage infrastructure. Right? You have to scale up and scale down. You have to do monitoring and failover, et cetera. You're doing a lot of DevOps before you even start running your algorithms. And again, as a developer, why do you really want to do DevOps? You really want to focus on building your algorithm, right? If you want to make any money at all, you have to kind of focus on protecting your IP, or at least finding a way to monetize it, or especially if it's something that's export that has restrictions or whatever, you have to deal with that part of it, license it, et cetera. You've got to deal with the data management. We talked about data being unstructured and all over the place, but you have to somehow get it into your application. So those are all things that you have to build. And then finally, you've got to build some user interface so people can actually use it. That might be an API, it might be a web portal, it might be a mobile client, right? By the time we're building all this non-analytic functionality, someone else came up with something even more relevant or more interesting in what we're trying to do, and the world moved on from the problem we're trying to solve. So all this great algorithm that we had, by the time we were able to bring it to market, it was too late. Somebody else did something even more interesting because we spent all this time building all the scaffolding when we really wanted to focus on building that distinctive analytic. So here's how you focus on winning, and this is kind of my one shameless plug on our software, but our platform actually has all the elements that you would normally have to build to actually bring an application to market, so you can really just focus on the analytic. So that, basically you decide, here's what I want to run, here's the data I want to run it on, heterogeneous data management already takes care of it. Here's the type of systems I want to run it on this time. Maybe next time I want to run it on different systems. The heterogeneous compute and the processing API take care of that. And by the way, I need a front end. I need a multi-tenant front end, right? Our portal or API takes care of that. And of course, it does accounting and billing and all the different things that you'd have to build in your application to bring it to market. So really what happens is you focus your energy on your algorithms. You don't worry about DevOps. You don't worry about orchestration. You don't worry about data management or UI work. Unless you really want to, you can build your own UI and then just plug it into the API if you really wanted to. You get on-demand access to the high-end hardware that you would normally have to, build very, very specific processes for. And because we actually account for what people use when they run your application, so you get paid automatically on a monthly basis. So you can really just do this, which is develop algorithms and earn revenue, right? And you have your data coming from your Internet of Things, your social media, et cetera. And then you basically spit out, in an on-demand way, prediction, prescription, et cetera, whatever it is that you're doing, because all you're worried about is your high-performance analytics running on different permutations. I mean, that's kind of the ideal way, where we add the most value as developers is in building those algorithms that are going to kind of solve the next big problem. Orchestrating infrastructure, not that interesting, guys. This has been solved 1 billion times. There's no need for you to do it again, right? Using somebody else's toolkit on top of somebody else's infrastructure to do it, that's just a waste of time and money, and it may not actually do it the way you want it to, et cetera. So what you really want to do is focus specifically on your analytics. So basically, to summarize, what we say winning the future means is obviously creating these unique algorithms that process the floods of data that are coming in, that solve huge problems, provide timely results, do not reinvent the wheel, right? Why do the same thing that you've done 1 million times just to run something new? Doesn't make sense. And by the way, get paid for doing it. So it's not just democratizing access to compute, it's democratizing the marketplace so that your customers, think about it as what the internet has done and kind of the home recording studio has done for independent music artists. They don't have to go to a music label in order to use a recording studio anymore and give up, they sell a CD for $16. They give up $15.90 to the record label. That doesn't happen anymore. You can go straight to your consumer now. And of course, you're assuming all these costs, but the costs are a lot lower because you have access to these resources. So what you want to do is be able to use a platform that gives you the ability to monetize your code without having to worry about publishing it and making it compliant and doing all these things, right? So we think that's very key. So in closing, I'd like to say onward and upward, and I'd love to answer any questions you might have. Yes, sir.
So when you use your algorithm, you just have to plug it into your system that's already there to actually to execute the code.
Great question, thanks. So what we provide environments that look a lot like machines. I mean, you log into them, it's a Linux environment, you build your code and you capture it. And then what you can do is you can run that in any different permutation on different hardware with different data and so forth. So you're not having to learn like a new universe of tools to build your code. It could be your very same, algorithm that you compile in your Linux system now. You're just doing it in an environment that can then be captured and run, via API on in different scale with different data and different processes.
And as Leo likes to say, don't be shy. Oh. So do you have an example of the sort of on-demand processing of real-time sensor data and providing real-time insights? Something that's running right now on Nimbix?
Do I have an example of real-time sensor data on Nimbix right now? Not that I can think of, but there is an example. There are. You've seen earlier from Paul's presentation, for example, of kind of near real-time processing of users inputting different parameters and getting results out that way. So it's not just all processing a large amount of data that already exists. It's maybe letting users play with a model and producing the data in real time, or near real time.
Yeah, and if I can just add to that, there's a couple of interesting use cases. We heard from the life sciences side of things, which is real time for sequencing machine output is actually more than adequate bandwidth to transition those inputs into a cloud-based infrastructure for processing. But actually, this week we have a customer, we're doing some latency testing on remote real-time sensing feeds coming straight in for actually machine learning processing and then pushing control outputs back out to the endpoint. So that's actually ongoing work today. There are some, sort of inherent challenges with real-time sensor input, and that is latency across the network, depending on where the compute lives. So good question, though. Question.
Great talk, Leo. I'd like to hear more from you about sort of the inflection point between distributed computing, say on mobile at the edge, versus the incredible power that you have here. And I assume it's going to be different for different applications. But what do you see the next few years looking like in terms of that mix?
Sure. I think you're seeing it today already. For example, at the last GTC I went to, they were talking about deep learning and using GPU, like massive amounts of GPUs in the cloud to actually produce matrices that you then download onto your mobile device and run it on its local, effectively CUDA cores that are obviously way more limited than what you have, on these big machines. But so you basically you train the algorithms in the cloud and you download the results of that and you let them actually execute on these devices. It still takes processing power, but it's not as much processing power as needed centrally. We're always going to have more power at our disposal in centralized locations. But imagine if, for example, you were doing speech recognition on a mobile device and you had to be connected to the internet for it to work, right? It wouldn't necessarily be that useful. It would be too much latency or whatever. You want it to respond just like that when you're talking to it. And that's what's happening with, being able to download these matrices, these devices. So we're still doing processing on the edge. I think, down the road, we're going to see more and more of that. I think one of the things about IoT that I think is very important is that we don't want to just send a raw feed of data up to the cloud. We want to filter it. I mean, that's a tenet of big data. It's capture and filter, right? So the more filtering we can do on the edge, the more manageable the data sets are, and the faster they're going to get to our central locations. We're always going to be bound by things like the speed of light and just kind of network congestion and so forth. And it's only going to get worse as more people use the networks, right? Because we turn around and make a network faster, and then within a couple of months it's already saturated. So the more processing we can do on the edge, the better off we're going to be when we finally get to that big horsepower to actually do the high speed analytics, right? Behind you, Steve.
Yeah, I'll just amplify what you said there on 2 points. First of all, I know many of the platform guys are already building what they're calling IoT gateways, and that's exactly the idea, right? So we're hearing that from Dell and other people. The other thing is, since we get pulled into a lot of high-performance multi-core stuff, the military has got some of these mobile devices now that are, they have a standard Android platform that's an 8-core platform, and they want to do a lot of bioinformatics processing and things like that, as you would expect, right, in some of the places they are, or in network denied type environments,
right,
more and more. So we're getting involved in a lot of those with the government ourselves.
Yeah, that's a really good point, because even if you have a satellite feed, the latency to get data up to a satellite is insane. I mean, you have to do the processing on the edge to some extent, right? So I think devices are going to get more powerful. Networks are going to get faster, but also more saturated. And then, of course, central systems are going to get more powerful. But we're just going to see more distributed processing as time goes on.
Other questions? All right. Thank you very much, Leo.
All right, thanks.